Okay, today we're talking about persistence and bifurcations of equilibria and nonlinear ODEs. In any case, we talk about the math behind it. So first, let's set the problem. I know I started last time something, but let's see what the idea is, and then we go into the math. Okay. So let's say we have a system that looks like x dot is f of epsilon and x. So epsilon is a parameter, okay? And, x, right, we want to find x of t, but of course, x will depend on this epsilon, right? So, for different epsilons, we get different solutions. So for instance, let's say we have something like, so here is an example, x dot is epsilon e at x plus x minus 1, right? So when epsilon is 0, okay, we have equilibria at x minus 1 is 0, so we have x equilibrium to be 1. Yeah, so it's right there. So the main questions now, if epsilon is not 0, but we jiggle it around 0 a little bit, right? Say it's small, okay? So like, I don't know, epsilon is 0.01, just a number, okay? The question is, are there any equilibria in this case? If yes, how many, right? If no, how come they disappeared, right? So it's something like this. So if we make a little picture, that's how people think about this stuff. Okay, so here is x, here is f of x. So for, there is 1, epsilon equals 0, if we draw this function, it would look like, so the right hand side there, here is y equals f of 0 and x, which is x minus 1. Yeah, and here is our root there, right? Our equilibrium, right? X equals 1. Okay. And now we jiggle a bit, we make it 0.001 or something, right? So if we do this, what happens, this graph moves a little bit. So we would get here, this green one is the graph for, let's say, f of 0, 0, 1 and x. So in this case is, well, whatever it is, I won't write it anymore, right? So, okay, let's write. Okay, so it's 0.01 e at x plus x minus 1. Okay, I'll just put it there. So here, if we're, we're doing it, we're going to discover, yes, this equilibrium is still here. So this would be the x equilibrium that shows up graphically, okay, for epsilon is 0.0. Okay. So I can do this, playing, if you want, with Maple or any graph that does, kind of, plots these functions, right? So now the question is, how come this equilibrium, still persists? That's the language you use, it still survives to these little perturbations of epsilon. So can we say a priori, just looking at the right-hand side here, at this function, can we say if this equilibrium will persist, or can we find some sufficient conditions that this equilibrium will still be there? And the answer is yes, we can. And we can actually, kind of think about it, with our own little minds and say, hey, if this slope here is non-zero, right? So this is, I'm trying to do it with a different color, okay? So let's do it with purple, okay? So here is the function, okay? So this is the slope of f of 0 and x at, right, this x equals 1, okay? And epsilon is 0, right? So basically, yeah, it's at 0 and x, right? So this slope obviously is not 0. And then, you know, when we jiggle a bit function and we kind of deform this original function, you know, we get into the green one, that slope will still be non-zero. Whereas if we have a slope that is 0, we can actually see that stuff starts happening in a way or another. And here is, I'm doing a picture. Let's say we would have something that where the slope there is 0. Okay, so here is a graph with the function. Okay, so let's say epsilon 0 and x. So this is a root here, an equilibrium. And then when we jiggle a bit, right, we make epsilon non-zero, this function will either go up and then there is no equilibrium, right? So no equilibrium, okay? No red dot if you're not cut with the, no cut with the OX axis. And here, right, on the other side, we jiggle it on the other side, we have two roots appearing, okay? So you can see that stuff can happen. And this is basically because the slope there, here, right, this slope is 0, okay? So as soon as the slope is 0 and we do a jiggling, and it could be go up or down, and then it's either disappearing or it becomes two equilibria, right? So what we can say for sure is that when, right, this slope is non-zero, then the equilibrium persists, right? We say that the cut is transversal, right? But what is this slope? Oh, this is actually df, a dx taken at the value where we started, right? At epsilon and x being 0 and xe, right? So if this is non-zero, then the equilibrium persists. So this is what I'm showing you. I think is very easy to understand on one hand because it's like first year calculus, but it's the fundamental of the theory for higher order, okay? And what we're going to start doing now is build the math theory behind these very, I think, simple ideas that we can see, these drawings, if you want, okay? That's how I'm building this thing, okay? So what we need to do to generalize this thinking to higher dimensions is to look at the, so here I'm going to write theory, and I want to do this in this course 1. We're going to do the inverse function theorem, well, versions of, and I'm going to do it actually directly in ND. I think I won't spend with 1D. Yeah. Okay. I think last time I mentioned 1D, so maybe I should put number 2 here, right? And then 3 implicit function, oh, theorem here, theorem. Okay, so that's what I want to do. And then again, I'll do it for 1 plus ND. That's how I'm going to build it. It's N plus M usually, but all right. So here is these two statement of this inverse function theorem. So it's like this. Let's say they have a function that is defined on a domain that is open of Rn, could be really Rn, takes values in Rn, and this function is continuous, differentiable, and with the derivative continuous on D. And we write this as a class C1. And then we take a point in D, and then we call B to be the value of that function in that point. All right. And then we assume, so if we have the determinant of the Jacobian of the function at a, so I'm going to write it as df dx at x equals a. So this determinant is non-zero. Then what is happening, I'll discuss a bit what is happening. There is a vicinity or a neighborhood, call it U1, of the point A, and there is a vicinity or neighborhood, actually not U1, just U, V of the point B, and there is the inverse of F defined on V, so it goes from B, it goes backwards, right, to U, as of class C1 on V. So this F minus 1 is continuous, differentiable, and the derivative is continuous on V. And moreover, the derivative of F minus 1 can be calculated and is the inverse of the derivative of X, thought as a matrix, right? And this is happening for any y in the domain of F minus 1, right? So in other words, we don't have to know the inverse function, but man, we can compute this derivative. Yeah, that's how interesting. And we'll see what an interesting application it has, because it gives us a way to approximate the inverse of a function that otherwise we don't know what it is, okay? So as an idea of proof, okay, so I'm going to make the main idea of proof. So I'm going to do it in 1D, and then for the general ND, you know, for the Rn, you know, n greater or equal than 2, then the idea is the same, but it gets more complicated. It gets into epsilon and delta like real analysis, okay? But the core of the idea is what I'm going to put down now. So let's look at the function. Here is, I'm going to draw a, right? So when I say 1D, I'm going to consider this one in R goes to R, okay? So that's what I mean. So here is a function. Here is this graph. Actually, I'll do the graph with a different color. No. Let's do it with green. Ta-da! Okay. And let's take a point. Here is that A. And here is that B, which is the value in A. Okay, squish it in there. B, F in A. Okay. And we know that the derivative here, so here we know that F prime in A, this is df dx, right? So if you want here, I can write this one like df dx at x equals A is F prime in A. And we know that this one is non-zero, right? So again, you know, it's slopey, you know, this idea of transversality. So let's put it in there. There we go. Right? The slope is non-zero. All right. So because the slope is not zero there, we know from calculus, if you want, or real analysis. Okay, so we know from this one that there is a neighborhood of A on which f of x is strictly monotone, meaning it's either strictly positive or strictly increasing or strictly decreasing, strictly monotone. In our picture is increasing, right? So in the figure is upwards, right? Because it's going up, okay? So here is this neighborhood. I'm gonna take it, put it here, from here to here. Right, we know for sure that this is happening. So this guy here is U1. And now because F is also continuous, then here it is, we get that f is bijection, right? Is one to one and onto on this u. And then because it's a bijection, this means that there exists f minus 1, its inverse, right? Defined on v, which we're gonna say it's f on u, the image of u goes back to u, right? Its inverse. Okay, all right. So we just showed that the existence of an inverse. So now, you know, the tricky thing is to show that this inverse is actually differentiable. Okay? So how do we do this? So is f minus 1 differentiable? Okay, so let's see this little bit. Okay, so what I'm going to do, I'm going to take a point in V, okay, and y near y naught, okay? So actually I didn't draw V, I can actually draw V as well, which is the image of U. Here it is, zoom, zoom, right? So somewhere, so this guy would be the V, okay? And now what I'm doing now, I'm discussing the differentiability of f minus 1, which I'm not drawing at a point in here. So let's say this is y naught, and then I'm taking a y somewhere near here, around there, okay? And what I'll do what I know I have to do when I have to do derivatives, right? So in any case, I know that I want to do f minus 1 in y minus f minus 1 in y naught over y minus y naught, and then take the limit as y tends to y naught, okay? But these guys are in V, so this means, because it's f minus 1, this means that I will have an x naught in U, such that f in x naught is y naught, and I would have an x in U as well, such that f of x is y, right? So this means that when I'm coming back here and I'm substituting y with f of x and y naught with f in x naught, and then I'm putting over y naught, I end up, I'll have to flip the page, okay? I'll end up, so f minus 1 composed with f is identity, right? I mean, that's the inverse. That's what the inverse does. So on the top, I'll get x minus x naught, and on the bottom, I still have y over y naught. Okay? Now I have to come with something else, right? So I have to flip the page though. I'm waiting for you guys to write. So I'm making a lecture like it's a math course, like it is a math course, right? G. Oh. Okay, all right. So we are here, right? So this is x minus x naught over y minus y naught. And now I'm gonna use down there, like in the denominator, that these guys actually are images of points, right, on the x-axis, right? Okay, and here it is. But our f is differentiable on that u, right? And x naught are in u. And then I recall a very nice, I used to love this theorem in my youth, okay? The mean value theorem, okay? So by the mean value theorem, there is a point psi, I have to use the Greek letter sign, okay? In between x and x naught and x. Now it depends how these guys, so without losing generality, I'm gonna take x naught and x greater than x naught. If not, it's the other way around, but the argument is the same. So there is a point psi in between x and x naught such that f of x minus f of x naught, okay, I won't have room for this, okay? Right here. Mean value theorem. Okay, such that f in x minus f in x naught equals f priming psi times x minus x naught. Okay. All right. So now I'm going to take this relation, let's call it star. Okay. And I'm going to put it here. So here, follow the arrow. Okay. So equals. All right. So I'm going to put it in there. Okay. I'm going to put it here. Oop, not red. X minus x naught over f prime in psi x minus x naught. Look what is going on. Look what is going on. Yay! Okay, so it's 1 over f prime in psi, right? And now we're going to take the limit as x is going to x naught. And remember, psi, right, is in between x naught and x. So it's somewhere here, okay? And now I'm squishing in this guy. Squish, 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 squish. Okay, poor psi is forced to end up to be x naught, right? We're just suffocated. Ah! Okay, so in conclusion, what we got that f minus 1 of y minus f minus 1 of y naught over y naught tends to, when x is going to x naught, if you want, 1 over f prime in x naught. But x goes to x naught is equivalent to f minus 1. Okay. So it should be that this one implies that f minus 1 in y goes, well, I don't want this. I want y goes to y naught, right? So that's right. Okay, so here, there's the argument. I'm looking for the right way to write this, okay? But x goes to x naught implies that f of x goes to f of x naught because f is continuous and differentiable. It's actually continuous is sufficient, right? Because it's f continuous. I'm trying to do it as clean as I can, which means that y goes to y naught, right? So in other words, here, this implies further that f minus 1 in y minus f minus 1 in y naught over y minus y naught goes exactly to 1 over f prime in x naught as y goes to y naught, right? And this is nothing else, right, but f minus 1 prime in y naught, right? Okay. So if you want, but this one here, let's do it like this. As you might say, oh, you know, you just skip here at the end. But this tends, as y goes to y naught, to the derivative, df minus 1, dy, right, computed in y equals y naught. So the derivative of f minus 1 at y naught is 1 over f prime in x naught. Okay, guys? So this is the proof for the 1D case, okay? Or anyhow, ideas of proof, because it's not completely clean, but that's how the flow goes. And then if one wants to do it for the general case in AD, the main idea is the same, like this kind of computation, right? And arguments. It's just, and you know, mean value theorem in higher dimensions. It's just that it's harder to write, okay? And it goes into, you know, that kind of notation that you do in real analysis, right? So you know, my purpose is not to do real analysis here, but, you know, to give you some ideas how things go, okay? All right, so this is for the inverse function theorem. And I said, you know, this is interesting because besides that, we're going to apply it for the inverse, for the implicit function theorem, it has some interesting application in itself by approximating the inverse of a thing. So I'm going to put here a note, okay? Okay, so interesting applications. Okay, so for instance, okay, so if you have a function that is in two variables and is linear, okay, so I'm writing here a function that I diligently cooked up this morning, okay. All right, so here 2, 3. So this is a linear function, so it can be written in this way. So it's basically of the form A applied to the vector x1, x2. Okay, so this would be A is a matrix. Okay, and provided that, you know, the derivative of this is non-zero, but we don't have to do this, right? By the way, what is the derivative of a linear function? I'll put it in your next assignment. Now it's too late to put it in this one, in the next one. Okay, you know that if I'm looking at for f of f minus 1 of y1, y2, okay, so this is obviously a function that goes from R2 to R2, yeah, okay. So if I'm looking for this one, well, it should have something to do with the inverse of the matrix A. And indeed, this is nothing else but A minus 1 as applied to Y1, Y2. Why? Because, you know, so F minus 1 of F of X1, X2, if I'm to do it, I know that any exercise I do with you, although it's simple, is not a wasted time. I already know this. Okay, so we'll just do this slowly. So this is A minus 1 as applied to A, to x1, x2, right? So this is A minus 1, A, x1, x2. So we'll end up with x1, x2, yeah? Yeah, it gets squished, not squished. Why would we squish it? Okay, so here A minus 1A gives us the identity, fine. Okay, so that's the inverse on one side, and F of F minus 1, x1, x2, oh, that's bad, it's y1, y2. So the inverse from the other side, this would be A minus 1, y1, y2, blah, blah, yeah, is y1, y2. So in other words, F minus 1 applied to y1, y2 is that one. I'm sorry, I'm writing on the vertical, on the horizontal as I see fit, okay? But it's the same object, it's the same vector x1, x2, no matter if I put it on the vertical or on horizontal. So in analysis, usually we write on the horizontal. In linear algebra, we write on the vertical, but okay. When it's important, we specify that we put the transpose, okay? But in this context, I think it's clear. So this is clear with, if I have to do the inverse of a linear function, it's just linear algebra. But what about if we have something that looks like this? X1, of course, I'm gonna write now a big sausage expression, right? Yeah, okay, there you go. 5x1 squared plus 3x1, x2 plus 2 ln x1 plus e at x2. I just had to cook something, right? And then here, 2x1 squared minus 3 sine of x1, x2. Okay. And then I'm saying, oh, okay, so obviously here we have a domain. So x1 has to be positive, yeah, because I put the ln there. Why? I don't know. I just put the ln there, okay? And then, you know, I'm going to say, hey, who can tell me what would be this? Okay, good luck. Because why I'm saying good luck, this is equivalent to computing really So it's solve all this stuff. I'll write it because I can write it fast, right? So all this stuff, right? So solve all this system for x1 and x2, okay? Good luck. So now I can let you solve this one and I can go and have a coffee. And if I would smoke, I would smoke a pack of cigarettes and come back and you still wouldn't be done, okay? So why I'm saying this cannot be solved analytically, actually, you know, it's what we call a transcendental equation, whatever. However, can we still say something about f minus 1? Can we approximate it? And the answer is yes. And the way to get the answer is applying the theorem that we just did, okay? So what we can do, okay, I'm flipping the page because I don't have space, but you don't have to, right? Okay. What we can do, we can say, oh, okay, let's calculate at one point. So, you know, I'm going to take A from the theorem to be, right? So this is a point, you know, like x1 and x2. So I'll take it to be 1, 0. So this is x1, 0, if you want, and x2, 0. Okay, so I'm going to put it like that. And B is f in 1, 0. So I calculated this morning. Okay, so it's 6 and 2. So these guys are like y1 and y2. Okay, 0. So there's the B. Okay. And now we have to do the determinant of df at dx1, x2, calculated at the point A, which in this case is 1, 0. Okay. So when we calculate, you know, the derivative, so it's determinant of df dx1, okay, df1 dx1, okay, maybe. Okay, I'll just put it here. So it's determinant of, okay, 10x1 plus 3x2 plus 2 over x1, and then the other one is 3x1 plus e at x2. So this is just derivative, the partials, right? Up and down with respect to x1 and with respect to x2. So here for x1 minus 3x2 cos x1 x2 minus 3x1 cos x1 x2. Okay, and then we have to do it at 1, 0. So we end up with determinant of 12, 3, 4, minus 3, and this is non-zero. Okay, you can skip this, you know, if you don't write as fast as I'm writing, just, you know, put there, because you have the notes and the movie after, right? Okay, so the point is that this determinant is non-zero, so this means that near 1, 0, there is f minus 1, okay, defined on a neighborhood of 6, 2, right? Goes into a neighborhood of the other one here. Let me, so this means that there is U, a neighborhood of 1, 0, and V, a neighborhood of 6, 2, and f minus 1 defined on V goes to U, that is differentiable in class C1 on V, okay? And the derivative, right, df minus 1, a dy, calculated at y being 6, 2, is the inverse, right? So will be df dx1 x2. Oh, sorry, calculated at the y. It doesn't have to be anywhere. Sorry. Okay. Is df okay, y1, y2, x1, x2 at power minus 1. Okay, that's what the theorem says. In particular, that's where I want to get. Okay, df minus 1, a dy1, y2 at 6, 2 will be 12, 3, 4 minus 3 at minus 1. Yeah, would be the inverse of this guy. Yeah? The inverse of this guy. I didn't write it again. Okay. We're going to say, okay, so what? Well, here is so what? So near 6, 2, we have the following formula. F minus 1 in y1, y2 is going to be F minus 1 in 6, 2 plus the derivative of F minus 1 in 6, 2 times y1 minus 6, y2 minus 2. And this is the linear, so it's approximately equal to this. And this is the linear approximation of F minus 1 near this point. Okay, it's nothing else but the first term in the Taylor expansion. Okay, so if I want now to actually put my hand on it, you know, I'll write another line saying, okay, so F minus 1 is such and such and such and such, right? So like we can write something like F minus 1 in y1, y2, almost equal. So that was F minus 1 is 6. It's 1, 0 plus the inverse of, what was there? 12, 3, 4 minus 3 minus 1, y1 minus 6, y2 minus 2, or F minus 1 in y1, y2 is, right, 1, 0 plus, and I used Maple this morning and put this, computed this, right? And whatever is this, right? So this is for y1, y2 near 6, 2. So this is the linear approximation okay, of F minus 1 near 6, 2. And I repeat, this is done not knowing what is F minus 1. That's the key. Yeah, this is exactly the key. We don't know what F minus 1 is, but we can say what almost is. Like in life, okay? Almost. We cook something, we want it to be perfect. It's almost perfect, okay? All right. Okay, so there's that. So now we go to the second item of the day, big item, implicit function theorem, which is so important that I had to do it for you guys, you know, including, again, a proof in the simplest non-trivial case, and then, you know, the proof in general, you know, expanded, whatever, with the right generalization, but not essentially the essence is there in this simplest non-trivial case. Okay, so here it is. Okay, where 3, implicit function theorem. I looked up for the number 3. Implicit function theorem. And I think these two theorems were done in multivariate calculus, but there is so much material that nobody has time to sit on it a little bit and actually digest it, you know. Okay, so here, so I'm doing the so-called 1 plus n dimensions. And why is 1? Because I will apply it for this epsilon perturbations thingies, okay? So let's say we have a function defined on D1, D2, which is the product of two open sets in R cross Rn, where n is greater or equal than 1, goes to Rn. And this is, again, you know, so it's something like epsilon x goes into f of epsilon and x. And this function, again, you know, is very nice, is C1 on this domain of it, okay? So differentiable with the derivative continuous. And then let's say that we have epsilon naught and x naught in this D1, D2. And let's call f in epsilon naught and x naught to be y naught, okay? And here comes the condition. So let's assume that the partial Jacobian determinant of df in the second argument in dx at some, I mean, at this epsilon naught and x naught is non-zero. Okay. Well, in these conditions, then there is a neighborhood, a vicinity of epsilon 0 and a neighborhood of vicinity of x naught and a function g that goes from u1 to u2. Okay, so this goes from an epsilon to a g of epsilon, yeah, which is C1, okay, on U1. Okay, such that F in epsilon and G in epsilon is still Y naught. Okay, so I'm letting you to write the statement, and then I'll make a picture for the statement, which is essentially the picture I started with today. Okay, sometimes people call this G of epsilon X of epsilon. So here is a picture for this kind of statement. Again, you know, so let's say we have F in R cross R goes to R, epsilon X goes to F of epsilon and X. And then we have this picture attached. And let's say we have F in some epsilon naught X naught to be some value Y naught. Okay, so here I'm going to put it Y equals Y naught. Okay, and F is some function. Okay, so this is Y equals F in epsilon naught and X. Okay, and the derivative we're talking about, so this is the value where F in epsilon naught X naught is Y naught, is like the equilibrium of ODEs. That's exactly where we're going to apply this, actually. That's why we're doing this, right? Persistence of roots of equations, right? Which we see as equilibria, right? And the derivative, that derivative we're talking about, that is non-zero, is exactly the slope here, right? This slope here. So this slope here doesn't look too good, huh? Okay, let me do it again. Now I can do a nice slope here. Okay, and go back to my red dot. Okay, so right, this means that df dx calculated at x naught, at epsilon naught x naught, is non-zero. Yeah, the slope is non-zero at that point. And now basically when we're doing what we are saying, you know, in the theorem, it says, well, you know, there is a neighborhood of epsilon 0, okay, which I cannot draw. And there is a neighborhood of x naught, which I can draw, right? So I'll make here a neighborhood here somewhere. It's x naught, and here is the neighborhood, right? That would be U1, U2, not U1, okay? And in this thing, right, there is, I will find the function g defined on U1 goes to U2. In other words, epsilon goes into a g of epsilon, such that f in epsilon g of epsilon is still y naught, okay? In other words, I can jiggle this function in green a little bit, okay? So I can jiggle it, maybe it moves a little bit, okay? So here is y equals f in epsilon and x. But then, you know, this cut with the height 1 naught will persist, will still be there, okay? And this guy here, we can give it a name. It's actually, right, at g of this epsilon. If you want, I can put this one epsilon 1. So this would be g in epsilon 1, let's say. Huh? And then if I take another epsilon and epsilon 2, I don't know, I will squish the picture too much. I'll get another root somewhere here, right? And so forth, right? So that's why people sometimes, instead of G, they call this fellow actually, you know, so it's a kind of a stress, you know, abuse of language, as we say, right? They say, oh, X goes into an X of epsilon. So actually, you're going to have F in epsilon, X of epsilon is still Y naught, right? But it's an abuse of language. I cannot call it X of epsilon, and unless I'm thinking, oh, this is like the G, right? And then they say the, you know, root of f of x, f of epsilon and x equals y naught, okay? So the root x naught, okay? Okay, persists for epsilon near epsilon 0 in a x of epsilon. See, it's an abuse of language, but what people mean is that when you jiggle a little bit the epsilon from epsilon 0, you'll still have their root of that equation. That's the point. And this is ensured by the fact that, you know, that slope of the tangent line is non-zero. Because if it's 0, as I said earlier, right, as I did that picture earlier, if the slope there is 0 and you start jiggling, then you get a different story, right? You don't know actually what you're going to get. So if here I have this, right, this graph, let's say, let's do it backwards like this, right? And then here the slope is 0 here, right? Okay, and the slope is 0. When you jiggle, you know, you might get 2 roots or you might get no roots. That's what it is. Okay, I cannot stress to you. So this is an application of this implicit function theorem. You know, I mean, I'm trying to give you a sense of where it's coming from, but you know, the applicability and the importance of this theorem, I cannot stress it enough, actually. Okay, so let's see how we sketch a little bit of a proof. Okay, so the proof is based on the proof on it's like a corollary or of the inverse function theorem. Actually, people do it, you know, sometimes some people first prove the inverse function theorem and they use that one to prove the implicit function theorem, whereas some people do it the other way around. They prove the implicit function theorem first and then they deduce the inverse as a corollary. So, you know, it's however you want to know. I did it this way. So here, I'm gonna put it here again because I want to see it. And you don't have to write it again, right? I just I like to see it when I'm writing because then I don't know. You know, if you would have a board, then it's different because I can save stuff on the board. But like this is not the same. Okay. Looking forward to write again on a board. Okay. df dx. Okay. At non-zero, and then there is u1 v of epsilon naught, v1 v of x naught, g defined on u1 goes to v1. The way I remember it is this way, such that f in epsilon, g in epsilon is still y naught. Okay, so this is, I'm gonna just write this. Okay, so that's the statement again. Okay, so here proof. Okay, and as I said, I'm doing it for 1 plus 1d, and for Riemann dimensions, the idea is the same. The notation and whatever generalization is, well, can be written, but is more complex. Okay, so here it is. And I like the proof actually. Let f be, so what I'll do, if you look here, this is an incomplete thingy. So we have here the domain is R at n plus 1, and the codomain is R at n. But the inverse function theorem works when you have the same dimensions of the domain and the codomain, right? So I'm going to complete the codomain with an extra dimension. That's the main idea. That's so here d1, d2 goes into R. Okay, so here I'm gonna specify that I'm doing d1, d2 into R cross R, and I'm landing into R. Yeah. Okay, so 1 plus 1d. So instead of this n here, I'm gonna take n equals 1. So let f be this guy, right? So I'm completing the codomain. Maybe I should write it like this, and then it's obvious. So this is in R cross R, yeah? And goes into R cross R. So here I have epsilon and x goes into, and now I have an extra dimension on the right-hand side, yeah? So in there, I'm gonna implement a nice epsilon, and then here is our friend f in epsilon and x. Okay, actually, here. Okay, so how do we write this? Okay. I have to make room for everything, guys, okay? So you don't do anything, I'll just write it again nicely, okay? So let f d1 cross d2 R cross R goes into R cross R. So here I have the epsilon and x goes into f of epsilon and x, which is epsilon and f in epsilon and x. Yeah. So let's put them one on top of the other. You'll see it exactly. This is the R, and there's the other R, yeah? Okay. So I completed the codomain with an extra dimension. So now I'm going, in other words, from R2 to R2. It's like the inverse function theorem. Okay. So we'll have that epsilon 0 x naught goes into f of epsilon 0 x naught, which will be epsilon 0 f in epsilon 0 x 0. So let's call this one to be, okay, we'll need some notation to go around, epsilon 0 and y 0, yeah? Okay. And denote f in epsilon and x to be, which is epsilon f in epsilon and x, to be uv, okay? Just, I need some letters on the other side, okay? Or if you want uy, actually uy would be much better, right? Uy, because I use y not for that one, yeah? Uy. Okay. All right, and this capital F is actually ready to work with the inverse function theorem. How come? So how was it in the inverse function theorem? It was determinant of df at its two, well, in this case, two arguments, all arguments, right? So determinant of the Jacobian, right? And this one computed at epsilon naught x naught. But what is the Jacobian of this function? Well, so we have d epsilon dx, not d epsilon d epsilon, d epsilon dx. So that's this guy, right? And then the next one is this one, right? So it will be df d epsilon df dx. So what is this? Oh, this is determinant of 1, 0, df d epsilon, and df dx at epsilon naught x naught. But what is this? Oh, that one there, right? When we compute determinants, right? I don't know how you compute determinants, but I know that I can cut this, right? In cross from the one, because I have the 0 on its right. So we just stay with determinant of df dx at epsilon naught x naught. But this one was given that is non-zero from where? Well, from the beginning, right? So the Jacobian of the capital F is non-zero. This means that we can invert capital F. And that's the key. We invert capital F, and somehow, you know, then we're going to do a little bit of mumbo jumbo, and we're going to be done with the stuff. Okay. So what do we have? We have a big capital F defined on D1, D2, R cross R. I'm going to write it again because I'm not lazy. R cross R, right? So it's from R2 to R2. And we have that F in epsilon 0 x naught is epsilon 0, F in epsilon 0 x 0, right? And this is epsilon 0 y 0. And we have that determinant of this Jacobian, df at the epsilon and x at epsilon 0 x 0 is non-zero, right? Then by the inverse function theorem, okay, there is a neighborhood of epsilon 0 and y naught. So on the other side, right? No, first we start on this side. On x naught, okay, and 1 on the other side. Okay. I have to be careful to not get dizzy with this. So 1 is the left, 1 is the right, and f minus 1 defined on V comes back to U, class C1 on V, yeah? Okay, good. And f minus 1 does what f minus 1 does, right? F of f minus 1 of epsilon and not epsilon, U. So we denoted, right? Okay, we had a notation on the other side. No, I think I denoted here, this one. So let's put a green star on it. So the notation was f of epsilon. Okay. And x was epsilon and y, right? Because I need it for the inverse, right? Because the inverse kicks this side, right? Kicks the y side. So here, epsilon and y, okay, equals epsilon and y for any epsilon and y in V1, not V1, in V. Right? I feel you all so excited about this. Come on, guys, it's a maths course. I know it's COVID and everything, but you know, I have to do some math occasionally. Okay, all right. Okay, so now let's see. So we're here, which is good. Okay, so now here comes a little bit of a interesting side. So this guy, right? When it comes back to U, which is in R cross R, right? So it has two components. That's my point. So then let's say that f minus 1 on epsilon and y has its two components. The first one would be a G1 and the second one a G2. Okay, right? So this is in R cross R, okay, the two components. So then we have that f of G1 of epsilon and y, G2 of epsilon and y. This is epsilon and y, right? Okay, I didn't do anything but argue that f minus 1, when it comes back, it has two components. But now f, right, in some epsilon and x, this is epsilon and little f in epsilon and x by definition, because that's how we defined the capital F. So when we put these two guys together, this means that, see, I'm going to substitute this, right, for, here, let's do it like this. So instead of the first epsilon, right, we have this guy. And instead of that x there, we have this guy, right? These are the entries in F. So now I can say, okay, so this means that, right, when I put these entries instead of epsilon and instead of x, I will get the first entry, which is G1 of epsilon and y. And then on the second spot, this thing, right? So epsilon is G1, so I put G1, right? Here's epsilon and y. Yay! Okay, so now this means, now equating, right? We equate term by term, if you want, or position by position. This means that G1 of epsilon and y is epsilon, and f in G1 of epsilon and y, G2 in epsilon and y is y, okay? But now this means, okay, so if G1 is epsilon, this means that f in epsilon G2 of epsilon and y is y, right? But then this G2 in epsilon and y is nothing else but a little right? G of, okay. So at y naught, okay, so I'm going to flip the page first. Okay, so let's write this on the other page. All right. So this means, okay, let's write it again to have it here, right? So we got here, G2 of epsilon and y equals y. And this is for what? For any epsilon and y in V, yeah? So now we're gonna do the following. Take y to be the y naught, the one that we had at the beginning. And recall, right, that y naught is fixed, right? So we had f in epsilon naught x naught is y naught, right? That's how we define the y naught, the level, right? Okay, so this means that f in epsilon and right is fixed, and y naught of course is in V because it's the image of that one. Okay, so here it is. Okay, and now let's baptize this as G of epsilon because y naught is fixed. So we end up with f in epsilon, G in epsilon equals y naught. And this is for any epsilon in that, okay, epsilon, okay, I cannot write it. I'm gonna write for any epsilon near epsilon 0 because this neighborhood here, this one is in the image of epsilon 0 and x naught. Anyhow, it's okay, it's good. So that's what we wanted to show. That's it. Yeah. Ooh, you're so excited. I'm so excited. Da-na-na-na-na, da-na-na-na. That was a song, and I was younger than you, I think. Yeah. Okay. So I killed you all with the theory today. Come on, it's not so bad actually. This is not bad math, you know. It's not really. It is some epsilon, but it's no delta. Let's just put it like this. So next time, so I'll stop here. This is it. Next time, we'll actually talk about applications of this thing, okay? And I want to show you something before, because now it's coming the juice actually. So why is this theorem important? Well, it has so many applications in applied math and in pure math, and so many things are based on it, okay? So I wanted to show you just before you go, here, okay, I'm moving to my desktop, and then if you look on Mass Overflow, right? Here, I was just Googling this stuff. And you say, okay, what is this good for? Look how many examples are here, 15 examples. And actually, I will put the link on YouTube, and I invite you to read, because this theorem is important not only for persistence of roots of equation, but to show that the function is a graph in manifold theory, in pure maths, in Nash equilibrium. It's like, you know, it's one of the fundamental results in math, and it, you know, it starts slowly, like you do it in calculus 3. It's based on inverse function in 1D, which is done in calculus 1. So things evolve, but then, you know, you get into this, it's like a carousel of applications, okay, like so many things. So yeah, I'll put this link there, and also I'll invite you to Google on YouTube, you know, as I say always, you know, there are probably way better lectures than mine in every subject, right? You know, so this is an important one, this one. Okay, so with this being said,